Gravity. Gravity is a force at a distance. So if you have a star a long ways away from another object, the star, the earth, whatever, then there is a force of attraction. They are attracted to each other from a great, great distance. It's a crazy thing, this idea of gravity, and that's our topic for today, gravity. Now, when we talk about the universe, turns out that there are 4 fundamental forces that hold everything together. Gravity is just one of them. And let's talk about them. The first one in this packet is what we call the strong nuclear force. Now, it's called the strong nuclear force because it's strong. Now, this happens inside of an atom. So if you're talking about an atom, it's in the nucleus of an atom. If you think about it, the nucleus of an atom from, let's say, a chemistry class that you took had protons in it, and protons all have a positive charge, and they should repel each other, and they do. But it's a very, very strong force that is exerted in very, very close proximity. The second force, but it only happens like at 10 to the minus 15th meters, which is very small. This force only happens to particles that are very, 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 very close together. So that's the first force that holds the universe together. The second one is called the electromagnetic force. And you've played around with this. This is that positive things are attracted to negative things repel negative things, and positive things repel positive things. So, but the strong nuclear force has to be greater than the electromagnetic force, otherwise the nucleus and heck all of the universe would explode. The third force, also happening inside the nucleus, is called the weak nuclear force. All right? And this, by the way, is in order of strength. The strongest, the second strongest, the third strongest. And then the last is gravity. Gravity is a very, very weak force, but different than, so electromagnetic force, by the way, is both attractive and repulsive. Does that make sense? Means that sometimes, attractive, a positive and a negative thing are attracted, and a positive, though, are repelled. And these are attracted, right? But a gravitational force is always attractive. It can only work when you are attracting, things are attracted to each other. There's no repulsive force. It's kind of a weird thing. So here's the weird idea, right? If you've got a person out in the middle of space away from all kinds of a gravitational field, a star or a planet or something like that, and you have another person right here, you know what gravity says is going to happen? It's because they both have mass, they will be attracted to each other. They will eventually meet each other. Heck, even if they were moving apart, what would happen is the gravity would eventually slow their speed of moving apart down, and they would come back together eventually. It's crazy. Gravity, though it's weak, it is exerted at incredibly large distances across the universe, which is hundreds of millions of light years across. So these forces happen very, very small spaces. 10 to the minus 15 meters, crazy small, right? It's inside the nucleus of an atom. And these happen over great distances. Super strong here, super weak, but over great distances. And as a note, also, I'm helping to fill out the paper that you've got in front of you. It is the force always pulls rather than pushing, if you will. Gravity is at a distance. That's the blank force. As opposed to a contact force, right? It's an at a distance force. There's 2 kinds of forces, forces that are contact forces and forces that are at a distance forces. These, by the way, are all at a distance forces. They are not touching. Touching is when you're pushing or pulling an object. All right, let's now take a look. Our sun and our planets and satellites were created by dust. In fact, how did the universe or our planet get together, right? Basically, we've got lots of dust particles out in the middle of the universe. And they started attracting to each other, and then they clumped, and they got bigger, and then this one came here, and they got bigger, and they got bigger. And it's the idea of how the sun and all that stuff, and how stars are born, if you will, is that little clumps get added to little clumps, and they eventually turn into stars. And yeah, that's how it works. So look at this thought experiment that we have right here. In this thought experiment, if you and your beloved are billions of miles away, and all of a sudden, I guess I already addressed this, and we left you out there forever and ever, will you ever meet? And the answer, of course, is yes, because two objects that have mass will come together eventually. There is a force of attraction. It's a force of attraction between two objects that have mass. So what is the force of gravity? Well, on the Earth, we've learned this before, on the Earth, the force, we know that there's the acceleration of gravity. We've learned that's 9.8 meters per second squared. So the force is equal to ma. So the force of gravity is just going to be the mass of the object times 9.8 meters per second squared. So if I weigh, let's say, 70 kilograms or whatever, you just say 60 kilograms or whatever that is, times 9.8, I'll round that to 10, that'd be 600 newtons. Notice I said I weigh 600 newtons. That is the weight of somebody, or the force of gravity on somebody on the surface of the Earth. It's different if you're further away from the Earth, but it's super easy to figure out what the force of gravity is on an object. You just take m times a, or what we often write is we write m times g, where g is the 9.8 here on the Earth. If you're on Mars or some other, that number will change. So when we're objects near the Earth, that works really well. When you're not near the Earth surface, it's different. We'll talk about that a little bit later. So the force of gravity acting on an object is more called typically the object's weight, which is what I said. Physicists distinguish mass. Now what is mass? Mass is the m right here, but that's the amount of matter right here. So the m is the amount of matter an object has and is measured in kilograms, right? We measure this in kilograms. And a force, F, is measured in newtons, of course. So we say this, by the way, you take m times 600, I did write n, but a newton, by the way, is a kilogram times a meter per second squared. That is the unit of force right there. But your mass, by the way, would be, so so if you were to travel to a different planet, what would happen is your mass would remain constant, but your weight would change because the acceleration of gravity would change necessarily. So if we have a 150-gram apple, right, so this is the sample example here, and it falls with gravity, what is the force of gravity acting on the object? So you would take 150 grams, but I'm going to say that's 0.150 kilograms, times 9.8, and we do the math and we just multiply it and we get 1.47 newtons, a little bit less than 1.5 there. So that's just multiplying those together. You could, by the way, said that the force of gravity, which this would be F of g, force, by the way, is vectorial. It's always downward. So you could say that it's negative. It's not that important. But because it's always pushing down. By the way, as a note, when I drop an object on the Earth, it falls. But I know here's the weird thing. It's the attraction of the two objects for each other. So when you've got the world and then you drop something down, because the world weighs so much more, so what's really happening is the object is falling to the ground and the ground is falling up to meet the world. That's a weird concept, but since the world weighs so much more than the object, that rock or whatever you're dropping, then there's no apparent motion of the world, but it actually is happening. So let's take this next section. When an object is in free fall and it does not necessarily accelerate towards the ground for its entire trip, the air resistance is large. So sometimes when I drop an object, like if I drop this rag from the top of a tall building, it drops. It has a downward force of gravity, but there's also another force pushing up. And the upward force is from the air resistance, right? And if it reaches a point where as it's falling, it reaches a constant velocity, which happens, by the way, quite frequently, it is said to reach what is called the terminal velocity. So if you ever watch skydivers, as they're falling, and then they're in that spread out position, what you see is you see them falling and they're actually moving at constant velocity. They're not accelerating they're moving towards the Earth, but not accelerating towards the Earth. And they can do cool tricks. And then eventually they need to decelerate, so they pull their parachute so that they land safely on the ground. So in this example, the question is do you want to draw the free body diagram of a 65 kilogram skydiver? So let's say I have a skydiver and just kind of put a circle around them because it's easier to draw it sometimes with a circle. Let me get a different color pen. So you have a downward force, and that's the force of gravity, which is equal to m times g. And then there's an upward force, and that upward force is air resistance, the friction F of the AR. And so we know that he has a mass of 65 kilograms. So this is equal to 65 times 9.8, which comes out to 637 newtons. And then this force from the paper there is 115 newtons, right? So what is the free body diagram? This is what it looks like as he's falling, and then you can figure out what his acceleration is by taking 637 minus 115 and plugging that into F equals ma and find his net acceleration downward. But then what happens when he reaches terminal velocity? We still have the same guy, right? And we still have gravity pushing him down at 637 newtons. But when the air resistant climbs to a certain point, when the air resistant equals 637 newtons, that is the free body diagram you would find for when he reaches at terminal velocity. Make sense? So those are the two free body diagrams that you can sketch. So folks, that's just kind of real quick ideas on how you can understand how gravity works. Remember, it's an attractive force, only attractive, and it's weird because it means that two objects are attracted to each other. So though he is falling to the earth, our skydriver, he is also rising, the earth is also rising to meet him, but you'll never be able to see that because the earth rises 0.001 meters, and he falls many, many, many hundreds of meters, even a kilometer as he's falling from the sky. Hey, Houston, we don't have a problem.